All right, everybody, good morning or good afternoon. Um, we today are going to be working through some Charles law calculations. And we've already talked about a few things to watch out for, such as the temperature conversions that you're going to need to do before you can solve for Charles law. Remember, they must be in Kelvin. And we're going to work through two problems, which are basically will represent the types of problems that you're going to see coming at you. Okay, so here we go. Let's get started. So first of all, we know that Charles' law is a proportional relationship between volume and temperature. If you increase the temperature, you increase the volume. If you decrease the temperature, you decrease the volume. So that's what we want to be thinking about as we go through these problems. What's happening to those molecules according to the kinetic molecular theory as we change the amount of energy that they possess? So if you cool them, they start to move more slowly, and they're not going to hit the sides of the container as often, so the volume is going to decrease. If you heat them, they're going to move faster, hit the sides of the container more often, and increase the volume. So keep that in mind as we go through these. Think through and try to visualize that. Okay, so let's get started with these problems. There's your Charles law formula. One thing that you're going to see is I'm going to be using quite often the conversion between Celsius and Kelvin. And remember, that formula is Kelvin plus 273. Okay, I'm sorry. Kelvin, let me do this. Let me do this correctly. Kelvin is equal to Celsius plus 273. So if you're given a temperature value of 100 degrees Celsius, what you're going to see me do when I record these, like say it's T1 and I'm given that it's 100 degrees Celsius, I'm going to write that down, but I'm immediately going to write plus 273, and I'm going to do the math so that I don't make any mistakes as I go along. So that would be 373 Kelvin. I immediately put that there, knowing that I'm going to use the Kelvin value, which is right here. Okay, so I would suggest you do that too, so that you don't make mistakes. All right, let's get started. We're going to use the same kind of system of problem solving that we have done before. We look at this problem and we realize that it is a Charles law problem. So I'm immediately going to write down, I'm not going to write with that highlighter. We're immediately going to write down the formula that we know we're going to use, which is V1 over T1 is equal to V2 over T2. Okay, now let's look at what we've got here. So we have a gas in a cylinder at a temperature of 120 degrees Celsius and a volume of 3 liters is compressed to a new volume of 1.50 liters. What is the new temperature inside of the cylinder? This problem is a little bit misleading, and it will make more sense if you think about it this way. Okay, so we know that the beginning temperature is going to be 120 degrees Celsius plus 273. So that's going to give us, for that one, a value of 393 Kelvin. Okay, so I immediately did that. So 393 Kelvin. Okay, and what did they do to this thing? Well, the volume changed. Okay, so the starting volume, V1, was 3 liters. Okay, 3 liters. And then the new volume, okay, you can see that right here. The new volume is 1.5 liters. Okay, and so then the question becomes, what is the new temperature, right? They want to know that. So that's T2. Now, so the question, like I said before, it could be a little bit misleading when you look at it because of all the information that you're given. So let's look at kind of a little drawing that I did to help me to understand what's happening. So we have the yellow gas in here. Okay, it's at 3 liters of volume. Okay, so this is equal to the volume, V1, right? And then the temperature was 120 degrees Celsius. Well, then something happened and the volume of the gas was decreased, right? If the pressure is held constant, what's the temperature going to be? Is it going to be higher than 120 or lower? Okay. Um, so think about it in terms of Charles' law. You started with a large volume and now you have a small volume. Well, we know that temperature and volume are directly proportional. So the only way to get a smaller volume like this is to have a lower temperature. Okay? So we should see a final temperature, T2, that is less than 393 Kelvin. And this works if you keep pressure constant, okay? So let's do the work and let's just see what we get. And it should be below 393 Kelvin, all right? Okay, so here we go. We're going to plug in the numbers that we know and we're going to solve the problem. Okay, so the problem begins to look like this. For V1, we have come on. There we go. For V1, we have 3.00 liters. And for T1, we have 393 Kelvin is equal to the new volume, which is 1.50 liters, right? I got that from right here. See that? Right there, okay? And then we're solving for T2, which is X. Okay, guys? So the problem's set up, and we're going to play the cross multiply game because we have that equal sign between fractions again. So here we go. We're going to multiply that, and that gives us 3.00 liters times X. And there's that equal sign. And then we're going to multiply this part of the problem, okay? And so when you multiply 393 times 1.50, what you get is 589.5. So definitely you're going to need your calculator for this unless you are able to do big number calculations in your mind. Now, one thing I want you to check out is what happens to these units right here, okay? Well, we multiplied them together, so you got to have them in here. Kelvin times liters, right? So that's what we've got so far, all right, from cross multiplication. So now to get rid of the 3.0 over here on the left, we have to undo it with division. And because there's an equal sign, got to do it over on the other side too, right? That's what equal means. And that's great because this cancels out. We have X. And look what cancels out over here. Liters cancels out with liters. So we only have Kelvin left. That's great. That's what we want. And so we need to do the math. So get out your calculators and do the math. And what you're going to get here, 589.5 Kelvin divided by 3, what you should get is 196.5 Kelvin. Now remember, we always want 3 significant figures, so let's round. 1, 2, 3. And so the answer comes out to be 190, add 1 to 6, right? 7 Kelvin. All right, so there we go. Let's look at it. We started at a large volume and we found this thing and it had a lower volume, right? And so the temperature, if you decrease the volume, the temperature should have decreased proportionally. And it did. It's less than 393. In fact, it's 197 Kelvin. Okay? There's your answer. Sometimes there's a curveball that can be thrown at you with these problems where they want you to give the answer in Celsius. Okay? So even though it's in Kelvin here and Kelvin here, you have to be careful sometimes when you look at these problems. They may say, what's the answer in Celsius? So in that case, we're going to convert it to Celsius real quick here just to show you how that's done. Okay? So this is a just-in-case situation. So I'm going to put this in a box, you know, like this is an extra. Okay, so I'm going to write extra on here. All right, so Kelvin Kelvin is equal to Celsius plus 273, right? So if the Kelvin is 197, we want to know what Celsius is. Okay. So how do we get rid of 273 when it's added? We do the opposite. We subtract 273. And if we do that there, we got to do this here. Okay. Right? And so let's do the math, right? So 273 minus 273, well, that's 0, so that's Celsius. 197 minus 273. I am sensing a negative number coming on here, so get your calculators out. Minus 273 equals negative 76 degrees Celsius. Okay? Well, let's look at what happened then. So we started at 120 degrees Celsius and we ended at negative 76. Ooh, isn't that cool? So if you can decrease the volume of the gas while keeping the pressure constant, you can drop the temperature, okay, down to negative 76 degrees Celsius. That's cold. That's just an extra, okay, an extra if asked for Celsius. Okay, I'm leaving that there for you. I put it in a box because I don't want you to get nervous about it. That's just a little bit extra in if you were asked to convert the answer to Celsius. Okay, all right, let's go to the next one and let's see how that works out. Okay, so we've got a balloon at a temperature of okay, you know what, guys? I see temperature, I see volume, right? Temperature and volume. Let's write down the formula then. It's gonna, of course, oh, I always do that. Of course, it's gonna be Charles' law. So let's get started with that. V1 over T1 is equal to V2 over T2. And so let's start writing down what we know. Okay. So for this one, it's looking that the balloon is at a temperature. So that's T1. The T1 is 191 degrees Celsius. So let's change that immediately to Kelvin so that we can use our relationship. And that comes out to 464 Kelvin. Okay. So that takes care of temperature 1. So there it is right there, T1. So what did we do? We cooled. Ooh, do you see what they did? You have a T2 now. You cooled it. What did you cool it to? 60 degrees Celsius plus 273, right? Equals, 60 plus 273 is equal to 333 Kelvin. Very good. The starting volume. Man, they're making this easy. The starting volume is 12.2. So that has to be V1, 12.2 liters. Okay. What will be the new volume? Okay, so what's the final volume? The new one, right? V2. There it is. All right. So we had a gas at 464. We cooled it to 333. So what do you predict the volume's going to do? Is the volume, if you cool a gas, does the volume get larger or does the volume get smaller? Hopefully you're saying, Mr. Ashley, according to the kinetic molecular theory, if I cool a gas, the volume is going to get smaller. It should be less than 12.2. All right, well, let's see if that works out that way, okay? So let's plug in the numbers. V1 is 12.2 liters. That beginning temperature is 464 Kelvin. And then V2, we don't know V2. That's what we're looking for, so we'll call it X. And then the temperature that we cooled it to was T2, so that's 333 Kelvin. Okay? All right, time for math, your favorite subject. Okay? So that gives us 464 Kelvin times X. And then on this side, we've got 12.2 times 333. That's a big number. That is 4,062.6. What about these units right here? Yep, got to put them down. Kelvin times liters. All right, let's solve it from here. We got to undo the multiplication, right? And if we do it on the left, because there's an equal sign, got to do it on the right. It's only fair. But it's great because look, this Kelvin unit cancels out, right? That's gone. Do the math. So 4062.6 divided by 464 comes out to be, get your calculators out, 8.755. And what's the only unit we have left? Liters. That's good because we're solving for volume. But we need 3 sig figs. So here we go. 1, 2, 3. Look at this number. Is it a 5 or larger? Yes. So we come out to 8.76 liters. There's our answer. Hey, not too bad, right, guys? Pretty much the same idea as the previous problem. Just instead of looking for temperature like last time, we were looking for the volume, okay? And so there you have 2 problems worked out for you for each of the different variables. So what are things that you have to be careful for, okay? So let's call these the watch out list. Okay, so the watch out list. Number 1, convert temperature to Kelvin. If you don't do that, you're going to be in trouble, right? So the Kelvin formula is Kelvin. Oh, Mr. Ashley, Kelvin is equal to Celsius plus 273. It's a nice little one to have for you. Number 2, make sure that you properly identify T1 with V1 and T2 with V2. Those are linked, right? You can't put T1 with V2. That will get you in a lot of trouble. So read the problem. They're usually fairly straightforward in describing what has happened. But if you have to draw a picture, like we did up here, go ahead and do it. All right, guys, so what have we done today? Well, we ran through 2 Charles Law problems. I gave you a problem where you solved for a new volume, which was the second problem, and I gave you a problem where you solved for a new temperature. And then I gave you this little extra bit here where you need to read the problem, because if they say, you know, solve for the new temperature and give the answer in Celsius, remember you got to convert it from Kelvin back to Celsius after you've got it. Okay, so that's it. Pretty straightforward stuff. Please refer back to these problems as you do your homework. You can pause it, you can stop it, you can rewind it, you can watch it over and over and over again, because it's the miracle of YouTube, right? You've got it at your disposal. All right, guys, have a good day and get started on those asynchronous problems.